want to talk a little bit about simple harmonic motion, Hooke's law, those kinds of things. First thing you need to be clear on is the period. The symbol for period is a capital T, and it's the time for one complete cycle. So it's expressed in units of seconds. So a good example of a period would be I start here, I walk, I go past my starting point, and then I return to my starting point. That complete trip, if I call that a cycle, it could take me 10 minutes. And that would be my period. Okay? The frequency would be lowercase f, and it's the number of cycles in a time unit. It's measured in hertz. And hertz is written as per second, or sometimes you see it as second to the -1. Same thing. Some people will also show you a cycle per second. Revolutions per second, revolutions per minute. Those are all frequencies. How many revolutions does it make in a minute? RPMs, a lot of us know about the RPMs of our engines on our car. That's a frequency, the number of revolutions per minute. So it's the number of cycles in a time unit. These two are related mathematically by being the inverse of each other. So if I know that it takes me 60 seconds to make one complete cycle, that's my period. My frequency is going to be 1/60th of a second. Let me rewrite that, 1/60th of a hertz, or I could say I've made 1/60th of a cycle per second. So it's going to take me 60 seconds to complete a cycle. It's like the second hand on the clock. If you look at it, it takes it 60 seconds to go around one time. So each second that ticks by, it's gone 1/60th of that cycle. Do not use something like this, because the period is not equal to 1 over the length. That takes us to a pendulum. So here's my pendulum. I'm going to pick it up and let it go. So I'm going to start it here. I'm going to release it. It's going to swing past, and then back over there. That is one cycle. Starting point. And then it swings out as far as possible. And then it returns to the starting point. Like one more spell. Returns to the starting point. That is one complete cycle. So for a simple pendulum, period of the pendulum, capital T, is equal to 2 pi multiplied by the square root of the length divided by the acceleration due to gravity. Or I can write it as 2 pi square root of L over G, and that's my period. Okay, so if they give you a problem and they say that the period of a pendulum is, let's go 20 seconds. And it's on planet Earth, so gravity is, I think y'all use 10 meters per second squared. And they want to know what must the length of the pendulum be. Well, here's my basic equation. But the unfortunate thing is I have a radical sign here, but it's really not any big deal. I'm going to square this side, and I'm going to square everything on this side, because I want to get rid of that radical sign. So I'm going to rewrite this as t squared equals, well, 2 squared is 4, pi squared is pi squared. The radical goes away if I square it, so that'll leave me a L, and then a G in the denominator. So if I'm solving for L, I'm going to say t squared times G equals 4 pi squared L. I'm going to divide by 4 pi squared. So L is going to be t squared G over 4 pi squared. It's the length of my pendulum that has a 20-second period. So I'm going to square my period. My gravity is 10 or 9.8, depending on what your class is using. I'll go with 10 because I think that's what y'all might be using. And I'll have 4 pi squared. Well, so I don't have to mess with this all the time. I punched it in ahead of time into my calculator. And anytime I see 4 pi squared, it's the same thing as 39.4. So 20 squared is 400. And I'll multiply that by 10. And I'm going to divide it by 39.4. So that's going to be 4 followed by 4 zeros, because 10 times 4,000 is 40,000, over 39.4. And I'm going to pause for a minute, and I'm going to find out what the length of that. Okay, now I want you to notice that these seconds squared will cancel with that, and I'll have meters here. So this is a ridiculously long pendulum. I got 1,015.2 meters long. But I gave you a ridiculously long period. I just wanted to keep the numbers nice and big and able for you to see what I'm doing with them. So is that realistic? No. A more realistic period might be 1 or 2 seconds. But it doesn't matter. You now know how to manipulate that equation to find out what the length is. If they give us a length of 1.5 meters, and they ask you what should you expect in the lab for that period to be, then if I'm on Earth, I know gravity is 10. So the math for this one is pretty easy. T is equal to 2 pi square root of L over G. Well, 2 pi is 6.28, because 2 times 3.14 is 6.28. My length is 1.5 meters. Gravity is 10 meters per second squared. So I'm going to pause for a minute and make that. Okay, so I took 1.5 and divided it by 10, and that was 0.15, and then I took the square root of that and multiplied that answer by 6.28. This came out to be 0.38 something, I think. So the period of this pendulum is going to be 2.43 seconds. So if I pull it out to the side, release it, and bring it back, it'll take 2.43 seconds for that entire trip. All right. Now if we talk about a spring, okay, M is the mass in kilograms that's attached to the spring and is going to cause it to oscillate. K is the spring constant. And that's a specific value for a specific spring. I think you did a lab over this, so it shouldn't be too surprising for you. If you hung a 50-gram mass on this spring, let me see if I can try to draw a spring. So there's my spring, nothing is hung on it. Now I take my 50-gram mass and I hang it on there. It's going to cause my spring to stretch. And if I pull this down, it's going to oscillate back and forth. You saw that in the lab. You could time it, and you could figure out the period by timing it, and then you could get the spring constant. There's all kinds of things you could do. So let's look at the math involved. If I just want the period, that's going to be 2 pi. My mass has to be in kilograms, so 50 grams. Remove the decimal 3 places. Is 0.050 kilograms. And I'm just going to make up a spring constant of 100. So I should be able to get the period. So I'm going to pause for a minute. Alright, so I messed up a while ago. I didn't get the recording going again, so let me go back and talk about this. This was t equals 2 pi square root of m over k. But I wanted to get rid of that radical sign so I could get k by itself, because that's what they want me to have. So I squared both sides. And that left me with t squared on the left-hand side, 4 pi squared. M is no longer under a square root sign. Over k, k is still in the denominator. So when I rearranged it for k, k was 4 pi squared m divided by t squared. So that's what the math looks like. Now I'm going to try to pause. Alright, assuming I did my math correctly, and I just have my cell phone for my calculator, so hopefully I did it correctly. 10.49 newtons per meter is my spring constant for my spring. Now, what if they said, well, that's great, but now I'm going to take a k of 100 newtons per meter, and I want the period to be 3.2 seconds. What mass must I attach to my spring to make that happen? So, same equation, the period of a spring is equal to 2 pi square root of m over k. I have to square both sides to get rid of that square root sign. So now I have t squared equals 4 pi squared m all over k. This time I want m by itself, so I'm going to have t squared k divided by 4 pi squared is equal to m. T was 3.2 seconds. K was 100. 4 pi squared is about 39.4. So that should give me the mass. Alright, so when I did that math, I got 26, right at 26 kilograms for the mass I had to attach to that spring. Alright, so let me see, I think I covered them all. Now let's do one more. Go back to the pendulum, and I promise I'll stop. So if the pendulum is not on Earth, so gravity is somewhere else, well, some other planet, and we have a length of 0.80 meters, and we have a period of, I don't know, let me just stop for a minute and think about that. Alright, so I'm going to let the period be 2.9 seconds. I want to know, what is g? Well, you have t is equal to 2 pi square root of L over G, but again, you don't want L over G. You want to get rid of that radical. So I'm going to get rid of it by squaring both sides. So now I have T squared equals 4 pi squared L over G. Or G is equal to 4 pi squared L over T squared. So now I have 39.4 because that's 4 pi squared. My length is 0.80. And I want to divide that by 2.9 seconds squared. So let's see, I'm going to pause it. Alright, so I got 3.75 meters per second squared for my units, and that is the acceleration due to gravity on Mars, and that's exactly what I was looking for. So I'm going to put this on YouTube. If you have any questions, ever need any help, I'm in room 2006. I get there at 7, well, I get there at 6, but you can get in the building at 7:15, and I'm there until 4:15 in the afternoon. Please don't hesitate to stop by.